When students are first trying to learn NMR spectroscopy in their undergraduate career, it can be, let's face it, an overwhelming topic. But for a lot of the early type problems that a lot of students have to do in NMR spectroscopy, say in an organic chemistry class, the early problems, getting your feet wet into doing this sort of stuff, it works best not to overthink it. A lot of students try to, read way too much into these things. And in the last video, I tried to indicate what I refer to often as your 5 best friends when you're learning how to interpret proton NMR spectra, because knowing basically 5 different, knowing 5 different areas of the spectrum and being able to look at it pretty quickly can tell you an awful lot about a molecule, and certainly get you started on a lot of types of problems where I call them either pick the structure out of the lineup, here's a spectrum, here's some possible molecules, which one is it, or a matching exercise where they might give you 3 spectra and 3 molecules and ask you to match them up. We're going to do examples of both of them because what I wanted to do is follow up that with some actual real live problems that I've either used in my own classes or seen in other textbooks. So first, a quick reminder of our 5 best friends when we are looking at a proton NMR spectrum. First, the aromatic region. And remember, 7 to 9 ppm. And that can vary a little bit. Other things can come in that range, but generally, 90% of the time, stuff in this area is from an aromatic molecule. Okay? So that's a good one to look at. Our second best friend, the alkene region. Approximately 5 to 7 ppm. And yes, that too can vary just a little bit, but that's generally the alkene region. Okay? Hydrogen near a heteroatom. Okay, near hydrogen near oxygen, or near nitrogen, near chlorine, near bromine. The area around 4, okay, approximately 3.5 to 4.5 ppm. Okay, this is a really useful area to see. Then the next one, shielded CH3s. Shielded CH3s, the area around 1 ppm, okay, give or take a little bit either way. These are the methyl groups at the end of a chain or something, and they can be very useful. And then 5th, broad peaks. These are hydrogens sitting on an oxygen or on a nitrogen, okay? Not the hydrogens near them, like this range, but sitting on a heteroatom. Now, these can have a broad range. They can stretch over a lot of the spectrum. But the key idea, they are broad peaks. They always look larger than the hydrogens attached to carbon. So they're pretty easy to spot. And so together, these 5 areas are really useful in being able to look at them pretty quickly and get a lot of information about your molecules. So what we're going to do is we're going to look at a few structures. Here are a couple of structures. What would we look for if, these structures, using our 5 best friends here, then look at the spectrum provided in the problem and decide which of the choices the spectrum matches up to. Okay? So here we go. Here are our choices. Okay? For the first problem, we have propanol. Okay? 1 propanol and 2 propanol. Now, right off the bat, you notice they are similar molecules, okay? But this one right here, this is critical, okay? Even before we start looking at our best friends, we note this one is symmetric. And that is very important. Right down the middle here, this molecule is symmetric. That's always going to lead to a simpler NMR spectrum and, groups of hydrogens, even groups of carbons, being equivalent to each other. Like the methyl groups at each end here are going to be equivalent to each other. That's critical. Okay? So what I'm going to do is we're going to look at the 2 structures and match them up to our 5 best friends when we're looking at proton NMR spectra and decide which one of these can help us when we look at the actual spectrum, decide if it's actually 1 propanol or 2 propanol. Okay? The aromatic region. Well, sadly, the aromatic region is not going to be of any use to us. Neither one of these molecules is aromatic. Okay? So that, of our 5 best friends, that one's not going to help us much. The alkenes. Well, not much help from these guys either. Neither one of these is an alkene. But hydrogens near a heteroatom. Now, these are going to work because we have this group of hydrogens. I'm going to draw them in. Sometimes students will see it a little bit more clearly if you draw the hydrogens explicitly here. Remember, that's a CH2 group. There are 2 hydrogens, and they are attached to a carbon attached to an oxygen. So this molecule, 1-propanol, has 2 hydrogens, okay, 2 hydrogens next to a heteroatom, next to the oxygen. The 2-propanol here, if you look at it, remember, this is actually a hydrogen. There is 1 hydrogen in that position. This one has a hydrogen right on a carbon next to the oxygen as well. But only 1. Okay? 1 hydrogen is going to be in this 3.5 to 4.5 ppm range. So right there, that is a big difference. And that will be enough to tell the 2 apart. Okay? Going on to our other best friends here, shielded methyl groups. Okay? Both of them will have these. Here is a CH3 group here at the end of a chain. Here are 2 CH3 groups, which themselves are attached to a carbon. And so these are relatively shielded methyl groups, but there is a big difference here. This is 1 methyl group, okay, that would integrate to 3 hydrogens. These are 2 equivalent methyl groups. That one is going to integrate to 6 hydrogens total. Okay? Another big difference between them. Broad peaks, hydrogens sitting on a heteroatom. They both have it, okay? And it's not a carboxylic acid, so it's not going to be way on the downfield side of things. Hard to know exactly where it's going to be. It's very dependent upon the solvent, very dependent upon how wet the sample is, but there will be broad peaks for both of them. But neither one of the, that is not going to be able to tell the difference between them. So out of our 5 best friends, 2 of them give us some really clear indications the things to look for. So what we're going to do is take a look at the actual proton spectrum given in the problem. Here it is. And clearly it's 1-propanol. Okay? We have a shielded methyl group there right around 1 ppm integrating to 3. We have a group of hydrogens right here at 4 ppm integrating to 2. Okay, clearly it's the 1-propanol. Okay, now remember I put a link to a PDF document of all the spectra that I'm going to show you, including this one here in the description for the video. Sometimes it's really useful to have an actual copy sitting in front of you besides the ones that I just simply show on the screen for a few moments. Okay, so please feel free to take a look at that and follow along. Now what I'm going to do is move on to problem 2. We're going to leave our 5 best friends up here, reset this, reset the molecules. Be right back. Here's problem 2. Okay, these 2 molecules. Closely related to each other, but ever so slightly different. So what we are going to do is, again, examine these 2 structures in light of our 5 best friends here, picking out what do we need to look for when we actually see the spectrum to be able to tell if it's this molecule or that molecule. And our first best friend, the aromatic region, and these are both aromatic molecules. Okay, so that is going to, yes, they are both aromatic. And there is a big difference here. This molecule has 4 hydrogens, 1 at each of these positions. Okay, 4 hydrogens. This one, 1, 2, 3, 4, 5, has 5 hydrogens. That right there, the integration of the aromatic region, the area around 7 to 9 ppm, that's going to be huge. Right there would be enough to be able to tell these 2 molecules apart. Of course, we only don't need just 1 piece of evidence, we need plenty. So we're going to continue on. Second best friend, alkene. Neither one of these is an alkene, so that one's not going to help us much. Hydrogens near a heteroatom. There's a big difference as well. This molecule does not have a hydrogen near a heteroatom. Remember, this is an aromatic ring. That carbon does not have a hydrogen attached. But this carbon, drawing in the hydrogens explicitly again, does. Okay? So this molecule does not have hydrogens near a heteroatom, so we wouldn't expect anything in the 3.5 to 4.5 range. This one does, okay, and there are two of them, yes, and there are two hydrogens, okay. So a signal in this range should integrate to 2 for that molecule, okay. Very nice difference between the two. Shielded methyl groups. Frankly, neither one of them has a shielded methyl group. This one doesn't have a methyl group at all. This one does, but it is on an aromatic ring, and that tends to move the chemical shift closer to the region of 2 or slightly higher, 2 ppm, and that's a very nice chemical shift to look at, but it is a crowded region. There's lots of other things that can go in there, so it's not nearly as easy to look at as the shielded methyl groups around 1. So I'm going to say that, for that, neither one of them has anything to that's going to be able to tell the difference. Broad peaks, hydrogens on a heteroatom like an oxygen. Yes, they both have them. Now there is a big difference here as well. This is a hydrogen on an oxygen as a part of an aromatic ring. It's part of a phenol. That is going to generally be pretty de-shielded compared to a alcohol like this one here, which is at the end of a little chain of carbon attached to a carbon here. And so this one will be downfield, far on the left side of the spectrum. And this one will be more upfield, okay? Middle to right side of the spectrum. Again, highly dependent upon the solvent and how wet the sample is. But there will be broad peaks, but I expect more downfield here, more upfield in that case. But these two differences here, these two best friends are really going to be the ones to nail it down. So as we did before, remember the PDF document is linked in the description. Here is the spectrum for problem 2. An aromatic region right there, just above 7 ppm, integrating to 5 hydrogens, and a group of 2 protons sitting there right at 4.5 ppm, right at the top of this range. Clear evidence that it's this molecule right there, okay? Now we do see a broad peak. Sure enough, it is, fairly upfield, and so we have that one in there as well. But the evidence is very clear. This is the molecule for problem 2. Okay, there. Pretty straightforward. Now, on to the third example. Here we have 2 hexene molecules, 2 hexene, 3 hexene. And right off the bat, we should make careful note, this one right here is symmetric. This one is going to give a simpler spectrum with things integrating to, instead of 3 together, integrating to 6, integrating to 4, integrating to 2. So that one, symmetry is always a big thing to look at. This one is not nearly as symmetric. Okay? And so, using our 5 best friends, let's see what we would look for when we take a look at this spectrum. Aromatic region, I love the aromatic region, but it's not going to help us here. Alkene region, alkene region, they are both alkenes. Here's the thing. They both have 2 hydrogens in the alkene region, but this one should have 2 signals integrating 1 to 1, okay? One for this hydrogen, one for that hydrogen. Let me draw those hydrogens in explicitly. This one should have 1 signal integrating to 2. Notice the difference here. Since this molecule is symmetric, okay, those 2 hydrogens will be equivalent to each other. Okay? And in the text I took these from, they are both implied to be the trans isomers instead of the cis isomers. So we're not going to worry about that distinction for a moment. But notice the difference. 2 separate signals integrating to 1 each. 1 signal, because of the symmetry integrating to 2. That's a big difference here. Hydrogens near heteroatoms. There are no heteroatoms in this molecule. So that we're not going to be able to make use of here. Shielded methyl groups. Yep, there are shielded methyl groups here. Here's a methyl group at the end of a long chain. Okay, so there's 1 that would integrate to 3. Now, this one also has hydrogens at the end of a chain. This one should have 1 signal, but integrating to 6. Okay, again, because of the symmetry. These 2 are going to be identical to each other. This methyl group back here on this molecule, again, it is not at the end of a chain. It's attached directly to the alkene. That's going to pull it more into that 2 ppm crowded range that is a little bit harder to use for making determinations like this. Okay, so looking at just the shielded methyl groups, this is the conclusion I come to. Okay, broad peaks, neither one of them have heteroatoms, so that is ruled out as well. So we have, again, two things to look at to make sure we nail down the proper structure. So once again, here is the proton spectrum. And oh, look at that methyl group right there at 1 ppm, integrating to 6. It is so pretty. And you notice there are only 3 signals in this thing, integrating to 6 to 4 to 2. Oh, yes, there's our molecule right there. Okay, it's a lovely molecule, lovely spectrum, and they're pretty readily done by looking at a couple of our best friends here. So there's problem number 3. Let's do problem number 4. Two fairly simple, straightforward molecules. One of them a carboxylic acid, the other with a ketone functionality and an alcohol over here in a different location. So using our 5 best friends, away we go. Aromatic region. I like it, but it's not going to help us here. Alkene region. I like it, but it's not going to help us here. Hydrogen's near a heteroatom. Now here is a big difference. This one, remember, again, drawing them in, has 2 hydrogens on a carbon right on the oxygen. This one has, that we'll expect a signal somewhere around 4, and it ought a 1 signal, and it ought to integrate to 2. This one does not. Okay, remember there's no hydrogens here on this carbon where the carbon double bond oxygen is. There are hydrogens over here, but they are not adjacent to the heteroatom. These hydrogens are attached to a carbon, attached to a carbon, attached to an oxygen. That is not good enough for this. So here, no, there will not be a signal around 4 for this molecule. There will be for that one. That's a big difference. Shielded methyl groups. This one has the shielded methyl group. Here it is, several carbons away from the oxygen. Okay, so yes, this one will have it, and it should integrate to 3. Okay. And this one, this has a methyl group as well, but again, it is directly attached to the carbonyl. That, as it will with some of the other examples, move it into that 2 ppm area, very crowded, difficult to distinguish a lot of things in there. So this one will not have a shielded methyl group. Broad peaks. Both of them have OHs on them, but there is a huge difference here. So they both have broad peaks. That is not unexpected. That is a carboxylic acid. A broad peak on a carboxylic acid, that is going to be somewhere between 10 to 12 ppm. That's going to be way down there on the left side. Very broad and, way downfield. This one is more of a traditional alcohol. It could be in a lot of different places. As always, it depends upon a lot of different things, but it's certainly not going to be this far downfield. So I'll just write in more upfield for this one. Okay? So definitely have some predictions that will allow us to make the decision. Once again, here is the spectrum. And oh yes, there it is, a shielded methyl group integrating to 3. Okay, we have that. There is no signal in the around 4 ppm. And there is a broad peak, and it's all the way almost to 12 ppm. Clear, incontrovertible evidence. There's our molecule. It's the carboxylic acid. Okay? So that one's pretty straightforward. Now the last one I have for you is actually a slightly different one. It's a matching exercise where on one page you're going to have 3 hydrogen spectra, okay, compressed a little bit to make them all fit on the page, and 3 molecules, and your goal is to take, for a spectrum, which spectrum is molecule 1, which spectrum is molecule 2, and so forth. So again, let me clear the board just a little bit, and we'll tackle that one next. Now we've got 3 of them to look at. So we have a collection of 3 proton spectra and 3 molecules, and we have to match up that, spectrum 1 is which molecule, spectrum 2 is which other molecule, and so forth. Again, our 5 best friends are going to really help us here, but this one is going to be one that requires us to use a slightly more intuition in our growing knowledge of NMR spectroscopy to be able to really nail this one down. It's kind of an interesting one. here we go. Aromatic region. Once again, aromatic region is not going to really tell us anything. Alkene region, same story here. Not going to be able to tell us much of anything. Hydrogens near heteroatoms. That we have, and here is actually a big difference. Each molecule has a group of hydrogens on a carbon right on the oxygen. Okay? This one has 2. This one has 2. This one, that is a CH3, has 3. That is a big difference. And so while we say, yes, there are hydrogens, in that 3.5 to 4.5 range, okay, there will be, yes, there will be there. 2 hydrogens, yes. 2 hydrogens, yes. 3 hydrogens. And in a matching exercise like this one, that right there is enough to be able to pick out one of the 3 from the set of spectra provided. Shielded methyl groups, okay? Now, there's a shielded methyl group here, okay? This is the one that's going to be somewhere in the range of 1. There's another methyl group here. It's on the carbonyl, not as useful, doesn't count here. Shielded methyl group here, shielded methyl group there. So frankly, they all have shielded methyl groups, but they're really not going to be able to help us distinguish because they're all, very similar to each other. Broad peaks. Now here, once again, we don't have the classic hydrogen sitting on an oxygen or on a nitrogen like we've seen in some of the other examples here. And so we don't have that to work with. So here's what I mean when we have going to need to use a little bit more intuition here. We have enough information from our friends in the hydrogens near heteroatoms to be able to pick out one of the 3 spectra, okay? And in fact, we're going to go ahead and do that now, and then we're going to intuit a little bit more on how to distinguish between the other 2. So here is the set of spectra. And if you look at spectrum number 1, okay, a group of hydrogens, 3 of them, all right around, just below 4 ppm here. Spectrum number 1, that's this one right there. Okay, that one is a pretty easy one to pick out. Okay, but these 2 are going to be a bit more of a challenge. Okay, and here's where our 5 best friends, don't quite take us as far as we need to go. Okay, but there is a couple of things to look for here. One of them is simply the methyl groups. Okay, now they both have a shielded methyl group, so that's not going to help us. But this one, and only this one, has a second methyl group. Okay, a signal that would integrate all the way to 3. This one does not. And so if we look at the remaining 2, spectrum 2 and 3, if we see another signal integrating to 3, then that is strong evidence that it's going to be this molecule. Spectrum number 2 has a peak integrating to 3 right there, just over 2 ppm. Okay? And so that is almost certainly going to be spectrum number 2. By the process of elimination and a matching exercise, then, we're pretty confident that is going to be spectrum number 3. Okay? But there is one other bit of evidence to extract out of all this, and that is this hydrogen here. That's an odd hydrogen. We haven't seen that one before, and it's not common that you see a hydrogen like that, a hydrogen sitting on a carbonyl. And so while I call these my 5 best friends, there are a few others that I keep in the back of my mind for referencing sometimes my special friends. And aldehyde, hydrogen sitting on a carbonyl, which is kind of what this one is. It's more of an ester here, but hydrogen sitting on a carbonyl. That's a little bit odd. Aldehyde is by far the most common functional group that will have that. No other functional group possesses it. And that is going to be almost certainly downfield. Okay? Traditional aldehydes are usually somewhere in the neighborhood of 9 ppm, okay? Right at the top of the aromatic region and sometimes just outside it. This one here, being a part of this ester, is going to be, you can guesstimate somewhere between 8 to 10 ppm here. And sure enough, if we look at spectrum number 3, there is a peak integrating to 1 right around 8 ppm. Okay? And so we would expect something a little unusual out of this molecule. And certainly spectrum 3, compared to the other 2, does have a very deshielded peak. So that just gives me even more confidence that that is most certainly spectrum 3. So keep all that stuff in mind. A lot of times, like I say, Students find, learning NMR to be difficult. I understand why. It is a complicated subject, but at least in the early going, when you're confronted with, here's a spectrum, which molecule is it? These 5 best friends can really help you start picking out molecules, picking out choices from various, here's a bunch of spectra, what structure goes with it here. And once you get kind of comfortable doing that, then you're in a much stronger position to actually start moving on to the greater skills of, looking at the spectra and determining from just that information what the actual structure is. So practice a few more of those. Get comfortable with these. It will help you. It will definitely help you a lot as you begin learning to understand and interpret NMR spectra. Talk to you later.